Yeah, this is a lab for next week. Okay, on Tuesday. We won't be able to have enough time on Tuesday to cover everything. I hope you guys can directly start working on it on the Tuesday during Tuesday lab. CNC is a traffic light controller. It used to be only 2 tasks. I just added another 3 tasks over there, but they are very similar. Instead of just using conventional logic, going through the data flow modeling method. I mean, it could work for very simple conventional logic like this. However, when it's getting more complicated, it becomes very difficult to find the logic expressions for every single signal output. So the best way is to use state machines, like the ones we have tried on Tuesday 2 days ago. It could be, it's also called finite state machine, right? FSM. It doesn't have a lot of states, right? It's just, it always comes back and goes to the initial state. So, but before getting into that modeling method, if we just look at this output, okay, it's a crossroad and have 2 traffic lights, actually 6, right? 6 lights, but 2 traffic lights groups, and it's green, yellow, and red on each side. So if you, we have 16 LEDs on the board, right? So we can definitely pick up any 6 of them as light 1 and light 2. So we have G1, Y1, R1, G2, Y2, R2 over here. And these are outputs, right? But the LEDs are outputs. So you need a decoder. You need certain inputs for certain pattern of outputs. If you start, because you can see all the states here is red, green, and red, yellow, right? And red, red. And after red, red, this one stays as red, but this one jumps back to green. It's green, red, and yellow, red, and red, red. So that's the entire cycle. And after this one, after red, red, it should be red, green, right? It should be red, green. But red, green is the same state as this one, as the first one. So it actually goes back. Okay, so we can cancel the last one. Okay, cancel the last one. So the idea behind the thing is if you use 3 inputs, battery inputs, you can form 8 different combinations. And if you count, and there are only 6 effective states of the LED outputs. So you only need 3 binary inputs for the decoder, because it's able to give you 8 combinations, and you only need 6. So it starts from 000 to 001 to 010 until 101, which is 5. So from 0 to 5, you got 6 states. And when you cycle through all the states, you could simply just add a 1 to this input. So we know how to add 1, right? We have formed the counter, which is every once it counts to a count max, depending on how long you want every state to stick there. Let's say 1 second, right? 1 second is very reasonable. Your eye can resolve it. You can differently tell the light patterns. So for 1 second, the counter needs to count to 100 mega, because you have 100 megahertz clock resource on the board. And once it reaches 100 mega, we clear the counter and we add a 1 to the input. So the input increase, and it goes to the next state, right, and show a different light pattern. So once you change the input, and this certain input has to form a specific output pattern like this, and this is a decoder, have to code up the decoder for this modeling method, even though it's not the easiest way or the best way. I'm going to show you the best way or easiest way from task 3 to task 5. But for the first 2 modeling method, we are using the data flow modeling method over here. So it's a decoder. Okay, we need to find out the logic expressions for each single output, as a decoder. So the table here on the right hand side are inputs. On the left hand side, the G1, Y1, R1, G2, Y2, R2s. All these are LEDs signal lines. They are directly shorted to the signal. You get a 1 here, the LED will be light will light up, okay, directly. So these are outputs. So this table here looks like a what? A truth table, right? It's a truth table, have input and outputs. And in that case, we need to find out the logic expressions for each single LED. So for G1, what is the logic expression for G1? Could you tell from this truth table? G1. For all other states, they are zeros, right? Only this one is a 1. So what's the logic expression to get G1?
0, 1, 1.
Yeah, 0, 1, 1. But for inputs, A naught BC, right? So be A naught BC. That's the ISO-P for G1. So we can get the first one filled out. Really simple. Y1, right, will be simply A, B naught, C naught. So on and so forth. So let's pick up the more complicated one, like R1, right? R1. So we'll simplify a logic expression. You got the truth table. The truth table is actually what you want, right? So when we fill up the numbers or the signal data, the data outputs for the truth table, we put 1 there because we want it to be 1, right? That's what we want. We put in the truth table. So truth table is usually the first step. You got the first step, and then you try to find this digital circuit out of it. So for R1, for all the other ones are pretty simple, only 1 signal line. But for R1, how do you approach it? What are the steps to get that done? So this is really hands-on, right? It's really hands-on. So after this lab, you guys can put a entry on your resume. Just say traffic light control on the IPGA board, right? Use a finite state machine. But this is just very simple. Task 1, task 2 are just very simple common logic using a data flow model method. You can say, hey, I used the data flow model method and finite state machine to model a traffic light controller on the IPGA board, right? But for this one, for the first method, you can see R1 has 4 entries. How do we approach this? R1 is what? So G1, Y1, we already got it. For R1, what is R1? Again, you have a truth table, and you are looking at the outputs. You want to find out the circuits for each output. You are looking at each column, right? Because each column is 1 output. Okay, so we already figured out G1, Y1. These are just separate circuits. G1 is just A naught BC. Y1 is just A, B naught, C naught. And R1 should be A naught, B naught, C naught, or we got here one more, A naught, B naught, C, A naught, B, C naught, A, B naught, C. See the flow of the digital design? It could be on the interview, right? They give you a real world example and ask you to model it in Verilog. So what are the steps, right? So first step is the truth table. Second step, the logic expression. And what's next and why? If you're capable, you can directly simplify it by just looking at it, right? A lot of times the logic expressions can be large, and it will make it very difficult to simplify. So we use the technique to simplify it. What is that called? What is that called? Wait, isn't a K map? Right? Shouldn't it be just K map? And so we have A, B, C like this. So it's going to be 0, 0, 0, 1, 1, 1, 1, 0. Why we directly jump from 0, 1 to 1, 1? Why?
So you're only like switching one bit.
Switching one bit. Okay. So which ones are ones? 0, 0, 0, right? 0, 0, 1. 0, 1, 0. 1, 0, 1. So you can simplify by grouping them, right? So if you group this way and this way, is the best way to group it? We're gonna do this as well. Why?
Leaves that one in the middle floating.
Leave the one in the middle floating. So this is called static hazard. It's a static one hazard. There will be glitches. The digital circuits they're not ideal. They have time delays. If you have this one, it's gonna get rid of the glitches or the spikes, unexpected spikes. So if you group them, you got an extra circuit in there, can get rid of the one static one hazard from the digital circuit. So let's see what are these expressions. Seems like we can simplify it to 1, 2, 3 instead of 4, right? It's not helping too much, but let's go through all the steps over here. So what are these? These two are what? So we're looking at, so C naught, right? It's not changing. And these two, we have B got toggled, right? B is toggled. So we only have A naught left. So this is A naught, C naught for these two groups, these two numbers. And for these two, A naught, B naught is not changing, and C got toggled. So we cancel C, have only A naught, B naught left. And for these two, looking at these two numbers, A is going to toggle, B is not changing, so B naught, and C, right? So that's the simplified version. Couldn't simplify this further. Okay, by looking at the K map, that's the result we got, and that's for R1. Okay, so actually true stable to this guy. Actually, you can directly from true stable to K map, and then to simplify logic expression. Okay? For R1, so be similar concept to G1 to R2, because R2 has multiple inputs. Definitely need a simplification over there. So you use the same method, you can eventually find out all the LED outputs, right? All the LED outputs, and these are 6 LEDs on the IPGA board. Okay, let's see how we can program it. So think about it. You need you just call it traffic light controller if you have a Verilog, just Verilog file, right? So you just need a one Verilog file, and you can place your traffic light controller and your top in the same file at the same time. It's not a big deal. So if I just start GVim like this, and I save it as something on the desktop, I just call it traffic light.v. Okay, and then because I'm presenting this, so I want to change the font size. It's going to be colon set GUI font equals asterisk. So I can have several options, and this font style is the most friendly one, but the size is not good. So I'm gonna directly type a, for example, 15, see if that works. It doesn't. So I have to make a bigger one. Let's do 20. Okay, it's better. And then colon set number. Right, set number. Insert module. Right. Traffic light. So this is the sub module, it's not the top. It's not the top. So what do we need for this sub module? What you think? What do we need? So as what we did on Tuesday, right? So we usually use a clock to synchronize everything. Even though seems like it's just a computational logic, why do we need a clock? Right? Because this is not running from top to bottom as a C program being stored in the program memory on the microcontrollers, right? So this is just a snapshot. After you synthesize it, implement it and upload it to the IPGA. It's like a snapshot. It's a digital circuits hardware. Because there's no instruction being taken out one by one and go back to a loop, right? So you need a clock to synchronize all the changes. Whenever there's a change being made, the clock will update everything. So you got a new signals to the output, depending on the input, or it's different states. All right, every clock cycle arrives, it updates the states. So we need a clock, right? Clock should be input. We can do that later, but just do clock. What else? It's just outputs, right? Because the sub module itself should be able to process all the inputs and do the counts and eventually output the LED signals. So let's do output, no, later. So let's do LED lights. I'll just call it light 1 and light 2. I believe we don't have to define the length over here. We can do it afterwards. Right, so how many lights we need for each light? 3, right? So it's 2 to 0, 2 to 0. And we can declare it here. It's actually, they have the same length. I'm wondering if we can, let's separate it, just in case. I just separate it. You know, even though it's not very necessary over here, but I just want to show why Vim is a lot better, because you don't have to use mouse, right? Once you finish the first one and you know the second one will be very similar to it, just do Y1 and P. Okay, and then you do a capitalized A and moves over there and change it to 2 and save. Okay, and let's think about that. So we have the clock to synchronize everything. The clock is running at 100 megahertz, and we want to change count, add a 1 to the input, because you can see the decoder has an input. It's on the website over here, right? So we're adding a 1 to the input every time. So the input is actually a three-digit binary number, right? It's adding a 1 every time to it. So should the input be a port or not? Should we assign the input as a port? I just think through this intuitively and logically. What's actually happening over here? So we are adding a 1 to the input of the decoder. Okay? We're adding a 1 to it every time. Do we need to make it a port? Which means, do we need a port for the input of the decoder for the IPGA? Are you giving a value to the switch to change it, or the traffic lights are controlled themselves automatically and running through the cycles by themselves?
They should be doing it on their own.
Yeah. You don't want to pay someone $50,000 a year just sit next to the traffic light switch it, right? So running through all the cycles by itself. Okay, so it's an internal counter, right? So that should be what? A register type. Okay, it's a lowercase o, right? You can start a new line and start typing. And how many bits? Three bits, right? Let's just call it in. Okay, let's call it input. We can assign an initial value to it. For example, we can give it it's a 3-digit binary bit. Just give a 0 to it at the very beginning, so it starts from 0. Actually, we should, right? But by default, Verilog will directly give it 0 if you don't assign an initial value to it. It's initially just 0, right? It's starting a 3-bit digital binary number, and the initial value should be 0. And because we want to set a timer, right? So it has to count to a certain number and then add a 1 to it, right? So we need a count max, and we're expecting 1 second it changes the light. So the count max should be a 100 mega, and it's a constant, shouldn't be changed. There should be a parameter, and let's call it count max. That's gonna be, we usually do a 32-bit, and decimal wise, it's gonna be 100 mega, 100 and 6 zeros. And I think these are all the parameters we need, or the variables we need to declare.
So we need a count.
Count as well. Yes, you're right. So count will be, let's directly follow the first one. It's gonna be a rag, right? It's gonna be rag, and will be how many bits? 32. And count, right? Yeah, by default it should be start from 0. All right. What's next? So you could have a combinational circuits, because all the efforts over here at the very beginning of the class to convert all these inputs to outputs as a decoder, and I have to code up the decoder for this modeling method. So in that case, you should do all the assigns, right? Assign what? G1. Wait, is there a G1? You don't have a G1, right? So what is G1 over here? Let's say light 1, 2. Which is G1, right? G1 equals what? A naught BC. A naught BC is going to be so A, B, C are in the in variable, right? So in that case, it's going to be in A naught, right? So A naught will be not into and in 1. Is that correct? Yep. So if you want to make sure it's correct, you could add a parenthesis for each one, but I believe it should work actually. Let's add a parenthesis so it's more readable. All right. Okay. So you can imagine that there will be how many lines of the assignments, or assigning all the signal lines to the outputs. It's gonna be 6, right? So you have 6 different lines, from G2, Y2, R2 to G1, G1, Y1, R1. So in that case, you could just directly YYP, 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 YYP. Yeah. YY is copy, right? And P is paste underneath it. So we can change it later. I will let you guys find out the log expressions and change it. So the thing is, these are static logic, right? Static logic. It's already fabricated, or not fabricated, right? Implemented on the IPGA. It's a hotwire. It's a hot piece of hotwire. If the inputs don't change, and the outputs are not going to change. So you have to keep updating the inputs, and they have to be synchronized by the clock. So you need always block to synchronize the clock, right? So you need to always block. Always post edge, begin, end, and do this. Okay. So what are the conditions over here? So should you start with if count equals count max? You should, right? If right, you have you have this, you have else. What you want to do in else? Count plus 1, right? Now let's go back to this part. So if count equals to count max, you should add a 1. So first count should be reset to 0, right? For sure. Okay, no doubt. Otherwise, you won't be able to count again. What else? How do you update the input? Add a 1 to it, right? You need to add a 1 to it. So add a 1 to which variable? In. Is this everything? What are we missing here? So seems like every time the clock arrives, it's gonna check the count. If the count arrives count max, which means to write a second, I'm gonna reset a count and add a 1 to it, so it updates the input.
You have to reset input to all zeros when you hit all ones.
But isn't it resetting to, oh yeah, so
I guess it'll wrap around automatically.
it'll wrap around and become 0 by itself, right? But would that work? Because every time it goes to 7, it resets back to 0, right? The 1, 1, 1 plus 1 is gonna be 0. It overflows, which is fine, but is that the ideal way to do it? Or is the right way to do it? You only have 6 states, right? It only counts up to 5. And the 6 and 7 doesn't have any corresponding outputs.
So you want it to wrap around when you hit 5?
Yeah, wrap around 5. So what else do you need over here?
Else if... Oh.
Or you can check. You can just directly check, right? If counter equals counter max, but we want to see if it reaches 101, right? So and in is not 101. Then we keep adding a 1 to it. So else if counter reaches counter max and in is 101, what's gonna happen? You need a begin end, right?
You don't need that count equals count max, do you?
It has to, right? If it's not equal to count max, I need to just add a 1 to counter.
Well, but
Else if
could just do if n is equal to 5, then reset it immediately and reset count. I don't think you need to wait for your counter to go up.
I think it would be the same output no matter what, right?
Yeah, but five also deserve a time, right? So it's a state. The light need to stay at that state for a second,
Okay.
right? And it gets into the OS block by every rising edge of the clock is running 100 megahertz. It's actually almost all the time. So you need to let it count to 100 mega.
Okay, I guess it'd be the same. Or you could make it, yeah, you could make your initial if go to 6 and just skip the count, but I guess either way.
Yeah, either way you can try it. But I think this will work as well. So if so this controls the 1 second thing, right? So it takes 1 second. So every second it reaches here. So to prevent from getting into these blocks before the 1 second arrives. So every time the clock rising edge arrives, only enters here to add a 1 to the counter until it reaches 1 second. It get into either one of them. If it satisfies this one, it's analogic. If it satisfies this one, which means already, so it's not reaching this state yet. It's going to be all the rest, the 5 states. So it's keep adding 1 to it. So at the very last time, it adds a 1 to in. So in immediately becomes 101, right? Because 101, when the next rising edge arrives, it's going to enter this block instead of this one. Okay, and enter this one, and also will wait for 1 second to display that state. So what should be in here? No.
Reset count.
Reset counter. What else?
Set it to 0.
Yes. Save. Any questions on this? Should be pretty clear, right? And what about the top? Module, traffic light, TV, of course clock, of course LED, of course, I mean that's it, right? And so we're gonna define input clock. And
Is this the test bench?
Yeah,
Or
test
is
bench.
it the top?
That's the test bench of the IPGA test bench, right?
Oh, okay.
Yeah, this is the IPGA top.
What's the naming convention for simulations then?
It's also top, whatever actually. Doesn't matter. It's usually you can call it top, you can call it test bench. It's the IPGA top or IPGA test bench, but TB, TP, top, whatever. Okay. And output, you only need a 6 LEDs, so you can do 5 to 0 LED. And then directly instantiate it. What's that called? Traffic lights, right? Traffic light, not lights, traffic light. And DOT. No brainer, clock, connect to clock. What else? Light 1, connect to LED 5 to 3. 5, 4, 3, right? 5 to 3. Wait, 5 to 3. Oh, sorry.
Open parentheses.
Yeah. Light 2, connect to LED 2 to 0, right? And close it. and close it. That's it, right? What else?
You didn't end the first module.
What's that? Oh, a module for the first one. Yeah. And I'm not going to run through all the synthesis. It takes a lot of time. I just show you how to add the project to it, add the sources to it. So this could be the solution for task 1, right? And for task 2, I mean the method to implement it is really silly. I don't really like it, but it's just one option for data flow modeling. Okay, so later on you can compare it to the finite state machines. But now here, the idea is that you can probably realize module. The rule, what's the name of the rule? I forgot, but it's the major rule on 160, and during the rush hours is actually the green light is longer significantly compared to the other side of the road. And so for that case, we want to control it during the rush hour mode. One side of the road should have a longer duration for the light, for the green light. So if you look at the truth table here, for instance, we want to keep. So after it reaches G1, right? After G1 is on, and R2 is on as well. So it's a red on one side and green on the other side. I want to keep this one for one more cycle instead of just 1 second. I want to do 2 seconds over there instead of 1 second. So if we're not doing adding any fancy stuff to the circuit, we can just simply add one more cycle to it and keep it the same state. So we're adding an extra one. So 0, 1, 1, we just add another 1 to it, but not changing the state, right? So it's just add a 1 to it, it becomes 1, 0, 0. However, the state is not changing, still green and red. So stays at the same state after adding a 1 to it. So you can simply add a 1 second to it. However, you can imagine you won't be able to customize the duration. It's basically just a 1 second. You could add another counter, but we're not adding too much to it because this is not an ideal method. So if we add a rush hour mode to it, and you'll have a new logic expression to handle, because you can see if I add one more state, it's actually counting to 6 instead of counting to 5 anymore. And you can see the outputs for G1 is changed. Maybe for the other ones will be slightly changed as well. So to find out the new logic expressions for each output, and then change your sign statement over here, change the logic. So let's assume that the logic has been changed already. Okay? The logic has been changed already. And we are adding a rush hour mode. And the rush hour mode, which makes sense to have someone to turn on the switch, to turn on the rush hour mode, right? So how do we do that? Add a rush hour mode. It's a switch, right? It's a switch. And it could be just the input, So that input, so for the sub module, now we already have a traffic controller module. It's a sub module, right? It's a Verilog module, and we just have one single input, make it available for the sub module, and we directly connect that little input to a switch. Simply, then we're done. So we're just looking at or checking that input. If that input is 1, then we enter the rush hour mode. Then we use a totally different logic and counting method, right? Otherwise, we follow the old method, all right? So you have to keep this group of logic over here, and then you create another a totally different one, let's say I'm gonna generate a different one. Right, this is for rush hour mode. Alright. But the logic will be different compared to the other one. And you'll need an input. You'll need an input here. Like let's call it rush. Okay. It's gonna be an input rush. And so for your test bench, you'll need a switch, and it's gonna be just one switch. Let's use switch 1. Okay, instead of switch 0. Switch 0 is gonna be being abused. Some of the switches are not working anymore. That's always the first choice for people to use. It's broken mechanically. And let's just use a switch here. So for here, then you wanna make a connection. It's gonna be rush, should be connected to switch 1, right? And this guy needs to be deleted. All right. So these are the modifications to the top, and some of the signal lines over here. So there must be something else we need to change, right? Let's see, what are they? Well, there's definitely not only way to do it, right? There are multiple ways to do it. And probably the no-brainer is that we just have two cases. You look at rush. So for rush case 1, we do one thing. So for rush case 2, we do a totally different thing. Does that make sense? So then let's just do it. So always can we directly do case after always? I think we can, right? But it have to be under begin. So into a case rush. If rush is 1. Alright, if rush is 1. No. So actually the first case is rush is 0, right? That's the original method. When rush is 0. And if rush is 0, then this definitely need to be wrapped in begin and end because there's so many lines over here. And we will need these ones to be here. Because case 0 requires one logic and case 1 requires a different logic. Okay? And because it doesn't like a sign in the procedural, which is always block, so you want to change it to, I want to delete a sign and want to add a arrow here as well. Actually, you can actually do this. I do a visual, right? Visual and colon norm. See how many characters you want to delete. 6, 7, right? 1, 2, 3, 4, 5, 6, 7. So gone. This save. So every time it enters this case, it do assignment. Right, depending on the updated ins. And then let's check this. So when rush is like that, we do assignment. Anything else we need to change over here? Are we done here for the major part of it for case 0? I think so, you know? Actually, sometimes you finished the coding in Verilog quicker than you expected. There's so many things to add it. But once you reach to some point, oh, it's done. Nothing else needs to be added. Do we need anything else for case 0? Except all the ends for begins, right? How many ends do we need? 1, 2, 2, right? Yeah, 2 more? Oh, 1 more, since we have one here already. Alright, give me end here. Anything else do we need for case 0? The case 0 is the older case. The one we did, right? So it should be right. We don't have to change anything over here. Okay? And assume that, you know what? Because I already coded up case 0 and case 1 should be very similar to it, I would just delete everything here. Alright? I'm gonna directly copy the whole thing of case 0. Okay, I'll do a Y. I'm gonna do a P and replace it with 1. So everything got copied. Because in a lot of cases, the Verilog modules are very repetitive. So that's why using Vim has a really great advantage over here. So case 0, now case 1 is the same as case 0. Definitely we need to change something over here, right? Also keep in mind, we didn't change the logic. You have to figure it out by yourself. Anyway, so for case 1, you have to look at the truth table over here and find out the logic expressions for them, and then update this part. Alright? But other than that, let me put it here. Do I need to change anything here for the rush hour mode? By looking at the truth table. So for the previous one, it reaches 5, right? So we're checking, hey, if it reaches counter max, and if it reaches 5, 101, then we do something, we reset it. But for here, we added one more state, so the maximum count is the maximum input is changing. So now it's 6 instead of 5, right? So what else we need to change over here in case 1? Change here, right? 1, 0. What else? Do we need to take care of this little delay here by your Verilog? No. Why? Why can't we use the same Verilog? Same if, else, if, and else. Same statement. But rush hour mode will stay at this state specifically for 2 seconds and 1. And we don't need to change our Verilog here.
Okay.
Except this guy. Why?
Green for a second, 1 second block, so it's just 2 1 second blocks, or it'll stay green.
Yeah. Because it's already handled by the truth table, right? Make sense? So that's method 1. So for method 2, I just save this guy. Right? I'm gonna start a new one. for method 2, it's going to be a state machine. Save it as. Okay. If you think about this project, it's actually very simple. And by using the data flow method for this small scale circuit, you can still find the logic expressions, but most of the cases, you just couldn't. There's no way that I can find the logic expressions to model everything under the data flow method, right? And for the entire circuit, it's basically just several states, right? Depending on the rush hour or not. So even for rush hour, it is still 6 states. Is it changing to 7 states? No. It's actually just 6 states. So the only thing is changing the time delay in the middle. If you just simply use different states, okay? And once it reaches one specific state, you just use a different count max. You have 2 different counters that just counted. Oh, actually it's 1 counter, but it count to a different count max. Then the problem solved. And you can just describe everything within the behavioral modeling method framework instead of thinking about the logic circuits. All right, I'm gonna start this coding and I'll let you guys handle the rest. Okay? How do we use state machines instead of using logic expressions, the data flow method? Think about it. I mean, it just outputs 6 LEDs, right? 6 LEDs and 6 states. That's all the outputs I have. It's the only things I need to care about. So why not just sorry. I just need a clock and I just need 6 LEDs, right? Just call it it's probably will be very long. G1, Y1, R1, G2, Y2, R2. I know it's not a good name, but so you are not losing. You always know which position has which signal line over there. So input clock and output has to be register type, right? Register type, and it's gonna be how many bits? 6. So it's gonna be 5 to 0. That's G1, Y1, R1, G2, Y2, R2. Okay, and you need a state. How many states do you need? 6. So 3 bits will be enough. State equals 3, 0, 0. I need a counter. Counter counts up to 100 mega. So let's do 32 bits. I'm using the counter max. It's a parameter. And that's a count max, which is gonna be 32-bit decimal number 100 mega. Anything else do we need? That's it. Now let's just code up the states. It's gonna be super simple and joyful experience to have compared to the first one. You know, because we have powerful tools, right? Powerful tools. So like in the future for AI robots, right? You just tell the robots to do something instead of thinking about how to do it. Like a boss. Always at pause edge of the clock. Begin. Get ready for it. Case, right? In the case. So you can put a case in the front of it. So case. So what are the cases you are looking at? State. State. So the first one is going to be this state. And then we can copy in the future, okay? So this state, what you want to do is at the 0, 0 state, and you are trying to, first I need to, so for each state, if it's not reaching counter max, I want it to stay, right? I want it to count. Yeah, let's indent it one more time. If counter equals counter max, what should we do?
Set count to 0.
Counter 0, no brainer. And what else? So counter equals counter max, which means it already has a 1 second pass. So we want to change the next state. So state should be state plus 1. But where do we assign the value to the output? It should be over here, right? Whenever it's not reaching count max, we're supposed to give our G1, Y1, R1, G2, Y2, R2, A data. We know it's a 6-bit. So what's the first state? R1 is 1. And G2 is 1. By looking at the truth table, see? R1, G2, right? R1, G2. So it's R1, so we get a red light on one row and green light on the other row. So it's like red and green, like that. And because we have more than 2 lines, we need a begin and end for this else statement, right? For that. Anything else do we need for that? If it reaches counter max, we move to the next state. If it's not reaching the counter max, we add a 1 to the counter and we show that state. That's everything. Done. And you think you still have to program it for 1 hour? Nope. Copy. Right? How many states do you have? 6. 1. Just keep doing it, right? 2. You need 3 more, right? 1, 2, 3. And the rest of the task is just simply go to the numbers and change the light patterns. You're done. Never, ever have to deal with K-maps and truth tables, right? But still truth table, but not K-maps and logic expressions. So behavioral method just have that advantage over here. And for the rush hour mode, you can imagine everything's being structured so nicely. So for the rush hour mode, what do you need to add to here? what are the things you need to add to here. I wouldn't just do it for you because it's pretty much overlap. You have to do something, right? So what are the things you need to add to this guy? It's going to be a different count max. So for the special cases, for a special state, you just replace the count max to count max 2. That's it. So the count max 2, you can modify it to 200 megasecond, 200 mega, 300 mega, or 500 mega, depending on your needs, right? Depending on how long you want the green light to stay there during the rush hour mode.
What if you just gave count max more bits and said if count is equal to like whatever n times count max?
Mm-hmm.
Is that
Shift count max.
Shift the count max. What does that mean? Or so it's just you set a number, set a goal, right? And then you start counting towards that goal. Doesn't mean doesn't matter what the length of it. So the length has to be able to handle the number, the size of the number. That's the whole point.
Yeah.
Yeah. All right, I have to let you guys work on the quiz.